We have mastered the art of harvesting energy. The sun, the wind, the water, we know how to catch them. But nature has a schedule we cannot control. The sun sets, the wind stops, and our grid is not ready. The StoreMore project is about one big question. How do we store renewable energy without locking our entire future to lithium alone?
Lithium-ion batteries are fantastic, and they are everywhere in our phones, our cars, increasingly on the grid. But they also have clear limits. They need critical raw materials, mining has environmental and social costs, lifetimes are not infinite, and very large scale, they can become expensive and vulnerable to supply shocks.
It is not just about raw materials. It is about time. A battery can power your house for a night, but what powers a city through a dark winter?
As a society, we can store the energy for a short term and we can play with it. But for the long term, this is one of the biggest challenges that we are facing. For winter, for seasonal use, we need to find out viable use cases.
We looked at 10 families of storage technologies: gravity, thermal storage, compressed and liquid air, hydrogen, flywheels, flow batteries, alternative chemistries like sodium-ion, ultracapacitors, even superconducting systems. We need a toolbox, not a single hammer. StoreMore helps to map the toolbox, compare the options, and show where they can actually work in real life.
The message that there are different energy storage technologies and they serve different use cases and they are not equal and not fully comparable one with another.
If we can succeed in timing consumption and production way better, we don't need as much storage options. So I guess it's really like a puzzle, and we have to solve all the pieces, not just one, not just battery storage or hydrogen storage or heat sector coupling, but we have to do lots and lots of things in order to succeed.
StoreMore was built as a Danube region cooperation project, so the structure reflected that. We had partners from 9 countries, from Germany through the Czech Republic and Slovenia, all the way down to the Western Balkans. Some partners focused on technical analysis, universities and research institutes. Others worked on real contexts and case studies. Municipalities brought concrete sites, rural communities, urban areas. And then a third group worked on an integration policy, creating a catalog of sustainable storage solutions.
Békés Csaba önkormányzata a StoreMore projektben konzorciumvezetőként dolgozik. És ugye a StoreMore projektben azért veszünk részt, hogy új utakat keressünk. A hagyományos lítium alapú akkumulátorok mellett más energiatárolási kapacitás megépítését kísérletezzék ki a projektben résztvevők. Alapvetően az Interreg Danube Európa Uniós forrásból táplálkozik a finanszírozás 80%-ban, 15%-ban a magyar kormány is támogatja a projektet, és 5%-ban Békés Csaba önkormányzata saját erőt is tesz be a projektbe.
Putem spune că suntem chiar pionieri cu energia verde, ținând cont că avem un parc fotovoltaic care funcționează în 2015. Mai avem un proiect făcut pe Huro, care este din nou primăria Oșorhei, unde funcționează astăzi. Este un proiect cu energie sustenabilă, primul proiect din România sau din Europa de Est care a avut panouri fotovoltaice.
This is a journey to find the missing pieces of that puzzle. We will visit the communities that are storing heat, the scientists drilling into the Earth's crust, and the engineers using gravity to hold back the dark.
My message would be quite simple. Don't let storage become the next bottleneck of the energy transition.
Our search begins in the West, in a small German municipality that decided not to wait for a miracle battery, but to use what they already had, the wind and the heat. Welcome to Fuchstal. Here the challenge isn't a lack of energy, it's having too much of it.
Fuchstal ist im Bereich erneuerbarer Energien ein Vorreiter in der Bundesrepublik Deutschland. Wir sind ein kleiner Ort, aber trotzdem schaut Deutschland auf uns, wo wir überall dabei sind, welche Projekte wir anleiern und welche Projekte wir gut in Betrieb genommen haben.
We have very special conditions also in terms of green energy. We have, the uniqueness that we have overproduction on energy for mainly solar energy, but also on water energy, because we have a river running through the whole district with a lot of energy production. So we produce more energy than we can use.
Here in Fuchstal we have two storage options. We have the battery system and also we have a heat storage system. So we use electrical power to generate hot water, which is being stored in a big tank. So I'd say battery storage, of course, is scalable. You just need more batteries. And the heat storage system just needs more space. Of course, it's scalable also, but in order to store the heat here, we already have like a big building. It's 18 meters high. It has 21 meters in diameter. So just for dimensions. Of course, if we wanted to store more heat, we'd have to build another big building for it.
If you have a heat sink or you need the heat, a heat storage makes a lot of sense. A heat storage is very good for daily use. If you regularly use the heat, which is a problem for household load in summer, for example, nobody uses heat in the summer, except for showering or something like that.
Und hatten das Problem mit Negativstromzeiten und haben dann versucht, die Negativstromzeiten von den Windkraftanlagen zu speichern. Wir speichern die momentan in Warmwasser und in einer Batterie und können dann bei Bedarf das in unser Wärmenetz einleiten. Die Bürger waren am Anfang skeptisch, vorsichtig. Inzwischen sind wir seit 15 Jahren im Bereich der erneuerbaren Energien unterwegs. Die Bürger haben sich daran gewohnt und die Bürger können sich auch bei uns finanziell beteiligen, sprich sie können ihr Geld investieren in unsere Windkraftanlagen und haben hierdurch eine sehr gute Rendite. Verbessert hat sich insbesondere der Bereich Wärmenetze. Die Bürger haben bei uns die Möglichkeit, ihre Gebäude ans Wärmenetz anzuschließen und ihre Gebäude mit unserer Wärme, die wir ans Haus liefern, zu heizen und müssen nicht auf eine teure Wärmepumpe oder Pelletsanlage umsteigen.
In order to succeed at a project, you have to be economically efficient. So the money you put in has to come out again. And I think that's the main problem right now, because those things are only produced in small scales. They're expensive right now. And so some of those projects still need funding. But if it's being shown that it's working and that it's successful, more and more things will be created, and it's getting cheaper and cheaper and cheaper, and then at some point it will be, and it is, economically efficient. This is what we've seen in battery storage systems. Now we can have battery storage systems with photovoltaic power plants, and they can be economically efficient in themselves, and I think this is going to happen for other good options as well.
Wir haben durch die Veränderung mit erneuerbaren Energien mehr Geld in der Kasse der Gemeinde, und das ist natürlich auch entspannter für unsere Bürger. Wir können uns mehr leisten als andere Kommunen, die keine erneuerbaren Energien betreiben. Ich kann allen europäischen Kommunen nur empfehlen, schließt euch zusammen, umso mehr. Traut euch in Europa, euch zusammenzuschließen und versucht miteinander voranzugehen. Nur so können wir was erreichen.
Fuchstal proves that a community can store heat if they have the right data. But what if we need to store power for industry? For that, we travel to the Czech Republic.
So we are in a small town called Litoměřice, and more precisely we are in the former barracks area where the army used to operate, and currently we are in the research center called Ringen, which is an acronym for Research Infrastructure for Geothermal Energy. When we talk about the energy sources which we use here or work on in terms of research, we basically deal with geothermal energy. This covers not only the shallow geothermal system, but also the deep geothermal system. And we try to combine the geothermal energy with other resources, renewable resources such as solar energy and solar thermal energy, and we try to integrate all these sources together. About what we plan to do is to drill up to 50 or 60 medium and shallow boreholes to store energy from the above ground, which is basically the waste energy which is generated from cooling, but also from the electrolyzer that needs also cooling, so provides lots of thermal energy. And we've got also the solar thermal panels on the roofs here. So the thermal energy storage will be based on the borehole thermal energy storage, the BTES as we call it. And this basically means that we will drill 40, 50, maybe even 60 boreholes in different fields. This will use the boreholes of 100 meters depth. But then we've got a medium one, which will be partially used for cooling down the electrolyzer. And the high temperature system will be based on medium deep boreholes up to 400 meters. And here we want to store the high temperature thermal energy, which in our case means 60, 70, maybe 80 degrees. So when we store it during the summertime, basically we will charge the storages during the summer season from May to October. And once the heating season starts, we will use the energy in the heating system. So that means that we have to use renewable energy for generation of hydrogen. In this system, we will use the photovoltaics, the solar energy, and electrolysis. So we will produce green hydrogen by using energy from the sun. But the, let's say, innovative approach is also that we will cool down the electrolyzer by the wells we will drill. So there will be kind of passive cooling of the electrolyzer. So we don't have to use electricity to cool it down as basically what is the normal system, let's say. So the group just visited pilot drilling site, which is funded from a European project, and we drilled, or we are still actually drilling, 2 pilot wells. One is a cored well to 550 meters, which we have this nice core from. And this will provide us key data for designing the borehole thermal energy storage. And the other well is slightly shallower, and it is 200 meters. It's a hydrogeological well. Again, it's needed for getting samples from the ground, but it's not the rock, but it's water. Because we have to know what is the underground water flow, for instance. So how fast the water flows under the ground, which direction. Because this is important, because if you store energy in a rock, then if there is water, then if is it moving, then the water transports the heat somewhere else out of your energy storage. So these are good examples how you can work together, because we've got international group with researchers from Germany, from the Netherlands, and other countries. And they will help us a lot with the research and interpretation. That's why the efficiency after some period in operation, some period of time, and during, let's say, 3 or 4, maybe 5 years of operation, then the efficiency increases. So we will start maybe with 40-50%. So that means that from 1 megawatt hours stored or pumped down, we will get 500 kilowatt hours. Whereas in 5 years' time, then we will reach much higher efficiency, as is the experience from other sites. But there are many indirect benefits. Our goal, the main goal, is to develop the site, develop the testing site for future. So once we construct all the technologies, they will start produce the energy. That's perfect. But the main aim or main benefit in the long term, let's say, is that we will find a way how to extract the thermal energy from the subsurface in a more efficient and safe way. And once we do it, then we can drill more wells and increase the energy amount we can produce. And that means we can reach up to 100% of the total energy consumption. This is maybe too ambitious, but it's feasible.
I'm responsible for managing the team of public energy experts, which are helping to the municipalities with their energy needs. It is quite a long procedure, but when you start with idea and you know about some financing model, you have to find some partners to create your proposal, and it takes usually some half year to write a good proposal, and then after you submit this proposal, you are waiting another 4 or 5 months to know the results, and then next 4 or 5 months to start the project. So from the scratch, from the idea to start of the project takes at least 1 year. So everybody are saying that we have to find new sources, new financial sources, and multi-level financial sources, not just from the EU, but the national, regional, and also private finances to support these innovative things. Because it will be big change in that way, that there will be not enough funding from EU side. We are cooperating with partners in Slovak Republic, Poland, Hungary, Slovenia, Austria, and Germany. Currently, we applied for some project also with German partners. If you will do it from the scratch for the big solution, like for example, the Ringen is, and Ringen has a long history already, more than 15 years is already here, and there will a lack of finance still, and they are lucky that it is one of the strategic project now, and finally they have finance. But if it will be local one, and according to the storage into water, and so it can be also cheap solutions, and then enroll it to the back. So don't focus on the strategic big project, but to take care and diverse it to the clever and better portfolio of solutions.
But drilling is just the start. To make this energy actually work for the grid, we need a digital brain.
My name is Michal Kuzmic. I'm the head of business and interdisciplinary collaboration at the University Center for Energy Efficient Buildings of the Czech Technical University in Prague. We are focusing on many technologies that make energy transition possible, and we are accessing the technologies from the user and operation point of view. We are focusing on producing energy and using it at the right time, and for that we need storage. Our research focuses on using, let's say, conventional storage like Lithium batteries and other types of off-shelf solutions, so to speak, and integrating them in let's say, complex solutions that offer different use cases. One use case is, of course, maximizing self-consumption. Other use case is allowing energy flexibility, trading on intraday or day-ahead market, or supporting the grid, the distribution system operator, or the TSO.
The term energy storage for me and for our research is mainly the energy storage for the sensor systems. So in this perspective, we are talking about very small energy storage that could be integrated somewhere into the electronics. And obviously also some renewable energy systems or sources which can power up the electronics, for example, in the buildings, but everything in the small scale. Our control systems that we design has to cope with the flexibility loads that are commonly used in the household as well as in commercial buildings. So if we design control systems, they also taking into account the flow of the energy to the grid, to the flexible loads, to the standard loads, and also from and into the batteries. In terms of the energy flow control, we might be talking about some elements of AI, but mainly as sensor researchers and sensor designers, we are talking about AI in terms of the anomaly detection, for example, on time series data, or on we implement neural networks on the image or on the videos. Those are the priorities, or those are the topics where we really use the AI.
We are mostly doing research on thermal energy systems, so it can be really different temperature levels, from very high temperatures of upper 600 degrees Celsius to more standard residential hot water energy storage. But it's not only thermal energy storage systems. We are also doing research on modeling of gravity-based energy storage systems, and also some different capacitors and flywheel systems. Okay, so basically every energy storage system has its own niche purpose and use case. So I think the reference always to the electrochemical battery is not always valid, because it's not always about just storing the energy when there is an excess of it and using it where there is a high demand for it. But it can be, for example, for clearing some peak demands for energy or very short bursts of energy. So there are different use cases for different technologies, and I don't think that the reference with the electrochemical is always valid.
We know how to bridge the gap between sunset and sunrise. But to keep a city running from November to March, we need a completely different kind of physics.
One of the teams looks into how to adapt for a seasonal storage, because this is the biggest issue. We can now, as a society, we can store the energy for a short term and we can play with it. But for the long term, this is the one of the biggest challenges that we are facing. For winter, for seasonal use, we need to find out viable use cases. For that purpose, we are looking into solid state or molten salt, different kinds of energy storage that can be utilized over seasons.
We are also doing research on long duration and seasonal energy storage. I think it's two different focus tracks. One is using depleted gold and silver mines for seasonal thermal energy storage. And the other focus track is researching hydrogen to be used as an energy vector for long-term energy storage. So we are doing our own experiments in the lab with high temperature packed bed thermal energy storage using basalt rocks for storing energy. Simulation and modeling is extremely important in our research, because it gives us an answer or a prediction of how the experiment will look like even before we start building it. And it saves a lot of money, and it saves a lot of effort and physical effort in building the experiment.
We are looking into integrating, for instance, hydrogen production into renewable energy sources. We work with Czech cities, we work with industrial companies, and the aim here is to see how, let's say, feasible and how economically viable these projects are. One of our bigger projects is, for instance, in the city of Litoměřice, where we are also using the geothermal potential of the very deep geothermal boreholes, while also producing locally hydrogen for further utilization in different ways, also for electricity, and using the waste heat that is produced during the electrolysis. As with any other new technology, new innovation, there is a so-called valley of death, which means that at the beginning of the market deployment, the market uptake of the technology, it needs to be somehow made attractive to the investors and compete with other solutions that might not be so efficient, but they might be cheaper because they are produced on large scale. So for this purpose, and this is very important for our work, we work in projects that are funded by European Commission, that are funded by national funding agencies, and also other bodies, all industrial donors. This is the way how we can really show the potential of the technologies, show that they are viable, test them in different use cases in operation environment, such as I mentioned, use for seasonal storage or energy flexibility for stabilizing the grid. And then in 1, 2, 3 years, they become more attractive to, let's say, ordinary or later adopters, investors.
I would say if the concept comes from the industry and they bring their own funding for a contractual research, it can be very fast. But more often the case is that the concept comes from our lab, and then it takes a lot of time to actually develop the idea in a project proposal. Then it needs to get evaluated and gets funded, for example, from some public funding or EU funding, and that can take a lot of months, sometimes even a year, before one can actually start on doing the research. So it really depends on where the funds are coming from. If it's the industry side, it can be really fast. If it's public funding, it can take a lot of time, and I see that as a major obstacle in bringing the innovation to the market.
Yeah, my personal opinion is that the support, the funding by the public money to, of course, storage or any energy systems need to evolve together with the technologies and with the needs of the investors.
Leaving the Czech labs behind, we head south to the mountains of Slovenia, where the storage isn't measured in rocks, but in millions of tons of water. This is the Avce pumped storage plant. It is essentially a massive water battery.
I'm Rajko Vovk, I'm technical director in Soška Elektrana Nova Gorica, which is the company which is power producer from hydro. Well, basically pump storage are used for more energy storage than batteries. It means that normally they last for more megawatt hours, and normally the price for those storage is lower than for batteries. But vice versa, batteries are better for short time and if you need very quick response in the system. Well, pump storage can be also very flexible, especially if it's variable speed like this unit here. We can change maximum producing to maximum pumping power in 10 minutes. And we can variate power quite rapid. It means in milliseconds for several megawatts. This is actual very fast, and we can also regulate voltage, of course. Well, because of a lot of solar installed, means that system itself needs more regulating and reserves power. So in past 3 years, we operate a lot of time during the pumping during the day. It means that when the solar produce a lot of energy, we can compensate with storage and help the grid also. At that time, it's also economy good for us because the prices might be also negative, not only zero. And during the nights and evenings when the demands are high, it's also very convenient for us because the spread is quite high. Round-trip efficiency in power pump station are between 70 and 80%. In our case, it's 75%. It means that whole round trip is a little bit lower, then it would be operating in optimal points because we are providing also ancillary services. So now in Slovenia, the project which will hopefully follow this one is on Drava region. Kozjak named the project. Problem is always when such huge facility comes to the environment, because people concerned about power lines, about reservoirs and things like this. But in our case, of course, we managed and of course made a lot of studies to cope with biological and environmental issues. Well, I believe strongly that Europe will need more such facilities, and this facility will be even more important in the future than it is nowadays. If the European Union is serious about green transformation, it should support such projects because these systems are backbone for this change.
Mountains are great for the grid, but to reach our homes and cars, we need chemistry.
So today we are at the Center for Development, Demonstration and Training for Carbon-Free Technologies. So the mission of the center is the establishment of a modern research and development environment through which we plan to research, develop, also manufacture and validate energy storage technologies. And the main goal of this center is to act as a bridge between the basic research institutions and the industry sector, and also to provide support in, say, shaping the policies for the decision makers, either on the national, regional, national, or even European level. The first barrier is basically the process. You have to master the process of battery production. The input materials have a relatively high price, which means that every percent of scraps or like material that is not usable for commercial use has a really high price, and that could be best depicted in the case of Northvolt, which was the most recent big battery project that went bankrupt. And this is also the technical aspect, which is the battery process, is also then connected to the financial aspect, which is, of course, as I mentioned, relatively high prices of the input materials, relatively high prices of the equipment that you need for production. Also, during the validation, testing, before you can actually start selling or commercializing your product, there's a lot of costs that accompany that. So without a strong financial background, I see a lot of difficulties in establishing big energy storage projects. So the technologies we are currently testing are based on the lithium-ion technology, more accurately the graphite-based anodes, and also LFP and NMC-based cathode materials. But in the later stages of our research and development, we are also planning to go beyond lithium-ion, and for example, sodium-ion, which is the next emerging technology and is the most common to lithium-ion. We also plan on maybe performing some studies on solid-state batteries, lithium-sulfur batteries, maybe even multivalent technologies such as magnesium ion.
So basically in Ljubljana we are covering TRL levels from 1 to 4, and here we hope to bring these technologies further to TRL levels 6 to 7, and which means us basically that we will go from, let's say, several hundred milligrams or grams to maybe kilograms, and go from very small cells with very small capacities to cells that could be practically used in some applications like electric vehicles or stationary storage. So basically the lithium-ion technology has been now in development for more than 30 years. So this technology has been optimized quite a lot, and currently also the price is very low. So it's very hard for other technologies to compete with them. So because Simply, they have not gone through such long process of optimization, improvement, and so on. So I think the main critical materials, of course, it depends on the country that you look from. But from point of view of Europe, I think it's lithium, of course, also graphite. And the thing is that we don't have very good access to these raw materials, and we lack also the capabilities to process them. So I think at the moment, this processing and also extraction capabilities, they are mostly controlled by China. So it means that whoever controls the raw materials can then also control the steps further along the chain.
So the most promising, the most mainstream right now is the NMC technology, which has the highest, we can achieve the highest energy densities with this active material. More recently, in the last year, there's a big, boom in the LFP technology, mostly because of its price, because the Chinese, mass production of these materials really dropped the price of these batteries. But the next emerging technology is the solid-state batteries. So the solid-state batteries promise around, let's say, double. In terms of the EV cars, solid-state batteries promise about double the range that commercial batteries can now achieve.
Solid-state batteries should bring main advantage in terms of safety, because we will replace the organic electrolyte, which is volatile and combustible, with solid-state material. And then the second big step in improvement should come through use of lithium metal, which would then also increase the energy density, both in terms of the gravimetric and volumetric. So basically, these batteries should be lighter and smaller. But employing these solid-state materials inside, it's quite a challenge. So it's a question if they're the next big thing just around the corner, or it will take maybe 10, 20 years to see them on the market.
In terms of stationary storage, maybe the, the most promising would be sodium ion. But since it's in commercial sense, it's still in development. So that's why in the short term, maybe LFP technologies would be more appropriate for that. But in the long term, sodium ion probably will have the primate over this section. Right now, we have a couple projects already being implemented, and there is a bit this distinction between collaboration with public institutions, governments, and of course the industry, because the public institutions are more interested. Let's say the research organization in Slovenia is more interested in basic science, and then how we can upscale the science that we develop to at least a prototype level. While collaborating with the industry depends on the partner. They have different needs. So mostly they would be either interested in testing and validation of the cells that they have or they produce by their own, or maybe just to get an in-depth characterization of the materials that are inside, so the active materials that are inside the batteries.
I'm personally developing multivalent batteries, so developing magnesium, calcium, and aluminum. And I see this also quite interesting in terms of long-term energy storage, because these are also very energy-dense reactive metals. But of course, I see the development of battery technologies as a race with many horses, and it's hard to predict which one will win.
The science is moving fast, but out in the real world, speed creates doubt, and doubt creates delays.
When it comes to the community, and even the engineers, electro engineers, there's a lot of skepticism for the batteries. But of course, we had a similar skepticism for lithium-ion batteries in 2016, 17. And this skepticism is now gone. It's like lithium-ion batteries are business as usual. There are a lot of them. They're growing at a fast rate. But some other technologies like solid-state or flow batteries are still something that haven't reached the potential itself, mainly due to the economy of scale. So lithium-ion batteries and factories that we have now in China and practically all around the world have scaled up, while for some other technologies the factories and the economy of scale is not there yet.
Az energia kérdése egyre inkább felértékelődött, nyugodtan merem mondani, hogy egész Európában.
Scaling the technology is one battle, but the mayors and engineers on the front lines are fighting a different war. A war against rules written for a world that no longer exists.
La noi este foarte greu să realizezi un proiect european, sunt pretenții foarte mari și cel mai neamănunțit lucru trebuie justificat cu acte în regulă. Birocrația foarte, foarte amănunțit, foarte multe acte, foarte multe documente s-a cerut pentru realizarea acestui proiect.
Igen, azt látjuk, hogy amikor egy ilyen bonyolult projektről van szó, akkor ennek a bürokráciája, a protokollszabályai is vaskosak, és nagyon komoly lépéseket kell tenni, előkészítő lépéseket, hogy megfeleljünk minden protokolláris elvárásnak. Azzal kellett szembesüljünk, hogy tervezésre előleget a StoreMore projekt kapcsán nem tudtunk igénybe venni, és azért azt látni kell, hogy ez a projekt komoly szaktudást igényel. Én nagyon komoly üzenetet szeretnék eljuttatni az Európai Unió irányító hatóságához, hogy az ilyen projekteknél legyen biztosítva a tervezésre, előkészületekre az igénybe vehető forrásoknak valahány százaléka, nagyon sokat segítene ez a jövőben.
Ca să fiu sincer, există și acum birocrație. Și ce nu-mi convine mie, sincer și spun, să dau exemplu curentul, să-l vând cu 1 leu, să-l cumpăr cu 10.
To break these chains, we need a new mindset. We need to stop looking for magic and start building a strategy.
A StoreMore projekt előremutató, innovatív megoldást fog majd kínálni a résztvevőknek, és hogyha a kidolgozott új megoldás tetszeni fog, akkor ezt egész Európában lehet, én azt gondolom, népszerűsíteni, hogy minél szélesebb körben legyen elterjesztve az az új módszer, amelynek a lényege, hogy a hagyományos lítium-ionos akkumulátorok helyett más megoldással lehessen és tudjuk az energiát tárolni.
We tried hard not to sell a miracle solution. Every technology in our outlook has pros and cons. Some are cheap but immature, others mature but geographically limited. Some are very clean but still expensive. Instead of marketing, we provided transparent comparison, the clear view of environmental impacts and raw material risks.
To understand how to unlock this future, we asked a simple question. If you could send a message to the European lawmakers, what would it be?
Don't be afraid to take a risk sometimes. So sometimes we have to implement a pilot project with a hydro plant, even though it's not economically viable, just to get started, to get the economics started and get the market started.
So my message would be make a plan, make a strategy, and then stick to it, because we have the expertise, we have the know-how, we just need a clear plan.
So I think EU policy needs to acknowledge that there are different types of energy storage technology, and it's not only electrochemical batteries. I think it's getting better, but for a very long time it used to be the case that it's only either batteries or nothing else, and it took a long time to get the message over that there are actually different technologies and they have different use cases for energy storage.
I think the EU can help in 3 very concrete ways. First, clear recognition of storage, including long-duration storage in legislation and market rules. Second, targeted funding for demonstration and first-of-a-kind projects. Third, support for regional planning and skills.
Trebuie să protejăm natura. Emisiile de bioxid de carbon trebuie reduse. Trebuie sprijinit stocarea energiei electrice. Dacă există acest lucru, atunci eu zic că vom avea un viitor mai bun.
I would ask you decision makers to do 3 things. Think in portfolios, not in single technologies. Support a mix of storage options matched to different timescales and sectors. Update the rules as fast as technology. Market design, grid codes, and permitting must keep pace with innovation, not trail 10 years behind. Use Europe's strengths. We have deep engineering, know-how, strong region like the Danube area, and existing assets like mines, industrial sites, and district heating systems that can host these solutions. If we get this right, storage won't just store energy, it will make our whole system cleaner, more resilient, and more European-made.
Renewable energy is the key
To a sustainable future.
It's time to invest in it today for a better
tomorrow.
We built the toolbox. We proved the technology. The only thing left to do is finally store more.